I'm gonna unmute so she can hear y'all now. Be right back.
They're trained to understand.
Hello.
Hello, Justin.
Hi, buddy. What would surprise you if, like, let's say you had like grandparents living in another state. I mean, I don't know if you do, but like they'd come over and be like, "Hey, it's a surprise." And Ozzy's just like, "Nope, you're I snug you."
Oh yeah.
Other state.
Oh yeah. How goes it, Miss Jocelyn?
Good.
Good? Yeah? All right.
My grandparents came over this morning because they lost power.
Oh no, really?
What are they?
How long have they been without power?
Since last night. It went out sometime last night.
Ugh.
Where does she live?
She's in Connecticut. So what was the temperature last night?
Oh.
We didn't lose power, but my dad's parents did. And when they woke up, it was 11 degrees outside.
Oh no, that is not acceptable.
My grandma couldn't put her clothes on because they were too cold.
Yeah, I know.
Probably bundled up and then.
And then what's even worse was my grandpa was setting up the generator so they could have things working. Yeah, the rope gave up and pulled right out.
No.
Did they go?
Mm-hmm. And that was the only way to start it.
Man. We have a generator hookup for our house, but we stupidly don't have a generator.
I would just use a
I'm,
fire. Just try to light a fire. We have logs in it.
Well, we
You
have
have a little
2
fire.
fireplaces, yes, but we have the generator and we need to get the generator hookup. Hold on, Miss Sen, you need something here.
But yeah, they came over this morning and we fed them.
Well, that's nice of you.
My sister made my grandpa eggs and I made my grandma a bagel.
Cool.
What if you fed them like cold, I don't know, ice cold cereal? That would be good.
Let me,
Oh my goodness.
what?
What is dog? Aren't we just leaving at 12 because we're doing it over?
Yeah, I told your mom that your dad,
And that's gonna pick me up when it's loud.
yeah, I mean, he could do that, or if you wanted to hang around and stay, we're gonna put Jackie up here on the TV.
Oh, I won't like go. Sorry.
Just because it's
Well, if it's like something I already know, I might be able to look at text them.
right.
Do some other schoolwork if just talking about something like answering a question there.
All right, let me get this for her real quick. Is that?
What is this? Can you sit on your head? Yeah, this is money.
Hello, where is it?
Is he too big to sit on your head?
What the heck? Hold on, Sonia needs a link again, so I'm just finding it real quick. I don't know why it's supposed to show up right here on this page, but that would be too easy.
I might be able to stay home alone tomorrow.
Ooh, what you gonna do? Have a party?
Mostly what kids do. Just
No, but I might be able to because my grandma has to pick up my cousin at around 11 or 10:30. My mom has an appointment at 9. My sister, my dad has to bring my sister to her 4-H thing.
Okay.
At 10. And so nobody's going to be left in the house besides me.
That sounds very busy. Your family's running everywhere.
Mm-hmm. And then what's even worse is tomorrow is when my friend Sam would usually come over.
Sam? Sam boy Sam, Sam girl Sam.
Sam, girl, Sam.
That's one of those names. You just don't know. Like mine. Gender non-specific, unless you see it written down. Sam doesn't matter if it's written down or not. All right, so I
My
hear
name was once just a boy name in the medieval times.
Jocelyn
There
was?
were no girls named Jocelyn. It was just a boy name. in
Really?
medieval
I did
times.
not know Jocelyn was predominantly a masculine name.
I think a lot of old names are just
Mm-hmm.
shortened or longened, just from the ancient times.
Yep. Yep.
What's even more unique about my name is my parents chose how it was spelled.
Yeah, I like that. You have the two ends. It took me a little bit to learn it, but it's different. I like your shirt, by the way. That shirt is epically awesome.
Thank you.
Mm-hmm. That's really cool. We're actually going to be doing batteries in a couple weeks. I was working on getting your stuff together for that. Yes, there's some things drying in the oven. All right, so I don't see the D'Antoni people, but they'll be here in a minute. So we can go ahead and start. Let me get my screen share up for y'all. And then we've got coming up, we're going to be moving to, who's that? Sky, maybe? I don't know. We're going to be moving into the last quarter very shortly here, like super shortly. We are almost there. And I've been working on that, getting your lesson plans out for you guys. So if y'all look, yeah, it's iPhone. If y'all look at where is we moving? Okay, so we're here today. We're lesson 25, right? And then we go to lesson 26. And at lesson 26, that's the last lesson of the third quarter. And
Wow.
then we're gonna move to the fourth quarter. So Jocelyn and Senya, you guys will be getting your Q4 kits from me probably sometime next week. And I'll make sure, all of this, obviously their lesson plan's already available to you, so you could start on it if you wanted. Come on, you coming? That's a good boy. That's a good boy. Yeah, he has to jump in.
Next week, I'll be going to Buford Tuesday and Wednesday.
Oh, okay. All right. What time are you getting to Buford on Tuesday?
We probably leave around 5 and 4.
Okay. Well, you're always so close by. Buford's just a hop, skip, and a jump from here. So you're back to dancing now? You're feeling good? Excellent. Awesome.
On March 9th, I have my last recheck, and they said it should be all healed by then.
Outstanding. That's great. That's a week from today, right? So perfect. All right. So we'll start our fourth quarter. And then the way the calendar works out, just the way things are this year, is we have lesson 27 and 28. And then we have a 2-week spring break because I always take off Holy Week and the Forsyth County spring break. So I try to align with what they're doing because everybody's schedule, if you're doing an activity, seems to align that way. And then we wrap up and the fourth quarter is really short. Hey, y'all, come on in, have a seat. The fourth quarter is really short because by the time we get to lesson, by the time we get to lesson 33, we're done. Lesson 32 is really the last lesson. Lesson 33 begins our study for our finals and our projects and everything. And then 34 is the last class. So we're on 25 today, right? So we are booking. We are moving along and nearly done. And did you shave the side of your head or is it just pulled back tight? I can't see. Oh, I was like, oh my gosh, that's a lot of hair. So no, okay, she's good. All right, so everybody's here and we're gonna go ahead, since everybody's here, and we'll go ahead and start. And you girls that are online, your lab is posted for you. I actually found somebody online who did nearly an identical lab to what we're doing today. So I'm sharing that with you guys because I don't see any reason to reinvent the wheel. It's already there. So that'll be that. Come here, I need to open that first. Okay, so here we are. We're talking this week about neutralization and titrations, equilibria, acids, bases, all this business. I also have a couple things to hand back to you guys. Don't let me forget. I'm gonna put them on the floor. That way I won't forget them. Yeah, because if there's something like that, you know how you do tricks to help yourself remember things? One of my tricks when I was in junior high, I learned, I was talking earlier, I had a loft bed when I was a kid that my dad built. It's like a bunk with no bed on the bottom. It's just a bed that's really heavy. Yeah, I loved it. And
my My friend Rowan has a loft bed.
They're so cool. But I would get all the way up there at night, get half asleep, and then remember something and be like, oh no, I have to do whatever tomorrow, and I'm not going to remember it.
I know.
So-
I have a bunch of scrunchies, and I'm like,
Uh-huh.
okay, put this scrunchie there for this.
There you go. You use a scrunchie. So what I would do is I would,
Set a reminder online.
yeah, I had a little shelf that was on the wall, and it was up high, so it worked with my loft. And it's where I kept my nighttime stuff, like, you know, my retainer box or whatever. And I would just take something off of it and just throw it towards the door, so that when I had to step over it in the morning, I would know that that was something I was supposed to do. Yep. All right. So moving on with this lesson today, we've got, come on, titrations. All right. We're going to be doing a titration in lab today that is a non-burette titration. And then if you remember, we had the burettes out last week, the big, tall things. We will be using them again in 2 weeks to do like a real old school titration. And they're super fun. So neutralization, this dog is licking my fingers. Yes, Miss Senya, did you put your hand up?
Yeah, it just cut me out for like a few minutes.
Okay, I don't think you missed anything important.
When she got added again, it showed 2 people.
Yeah, it did. No, I think, yeah, she's back. Yeah, you froze and then you came back. We were just talking about starting the lesson and how we're going to be doing titration with burettes in a couple weeks. And this week's titration is a non-burette titration. So
Okay.
what's neutralization? We have neutralization reaction, right? So a neutralization reaction is when an acid and a base mixes and acids donate protons to the base. And that's called a neutralization reaction. Remember that acids are proton donors and bases are what? Proton acceptors, right? Now, at the end of this lesson, I'm going to go over with you guys for real quick, if we have time, a little review slideshow I made because you guys are wrapping up Unit 7 today, which means you have a test, right? There's a test. Yep. No, online, just like usual, but there's a test. So I've put a slideshow together for you, and I'll send it out to you so that you guys can study from it. So when there is a neutralization reaction, the final pH depends on whether the excess ions at equilibrium are due to the weak acid or base combination or a strong acid and base combination, but you're usually getting closer to 7, right? Now, if you had, say you had equally strong acid and equally strong base, and you put in 3 parts of acid and 2 parts of base, you would end up with a final product that was still acidic, because you had more equally strong acid to begin with, right? And then if you do it the other way, say you had a really strong, equally strong base and an equally strong acid, you put in 5 parts of base and 2 parts of acid. In the end, it's going to be more basic, right? So it depends on where the ion equilibrium is at the end, where the ions are at equilibrium. And equilibrium will be when everything stops moving back and forth and all the neutralization that's going to happen has already happened. So here is a graphic for neutralization. So it occurs when an acid and a base react together in correct volumes. So there they are pouring their acid and base together. And what do they always produce? Drew.
Well, not wait, are they both? Is it like both the same amount?
Yeah, in this case, we're assuming they're the same amount, same stream.
Well, you got water, fresh water with salt at the bottom.
Yep, water and salt. And if you have the right volume and the right strength of acid and base, you will end up at 7, your pH at 7. So in this case, they're combining sodium hydroxide and hydrochloric acid, and they're getting water and salt, right? Sodium chloride. Isn't that what we did last week? Wasn't that last week, that one? No, I don't know. I have filmed and put together so many labs in the last 2 weeks. I can't remember which ones we've done and which ones I've done in my head. So I've just done so many of them. So I love this. If you look in your textbook, which was written for the US, it'll tell you that neutralization, that happens in the US, but neutralization happens in the UK and probably Canada. Do you see the difference? What's the difference of those 2 words? The S and the Z. Yeah. Have you noticed that a lot of things that are British and sometimes Canadian will have S's where we use Z's? They do it all the time. So if you see it written with an S, it's talking about the same thing. It's just taking a British spelling. So neutralization happens in the US while neutralization happens in the UK and probably Canada. There's a bunch of stuff like that where the spell, like color. You've seen how they spell color, right? We spell color C-O-L-O-R. How do they spell it?
They do U-O-U.
Colour is how they spell it. And they, and not just words they use differently. Yeah, I know, but the way they spell things. So they use words differently. Do you know what they call the trunk of a car in the UK?
Oh wait,
Do you remember?
my cousins are.
It's called the boot.
Yeah, the boot.
And
My cousins are Canadian and I'm a Canadian.
uh-huh. Do you know what they call the like a truck, like a delivery truck? A lorry. Yeah. And they
My
call
cousins are British, but like they live in the U.S. now, so they normally.
mm-hmm. And like we have what we typically call a powder room, which is like a bathroom without a bathtub in it. It's just a toilet and a sink. They call that a water closet or a WC, or the loo. Yeah, such good things. So neutralization versus neutralization. So
Jamie,
yes, ma'am.
instead of having lesson lab 25, I have 2 lab 24s.
Yeah, that was a typo. Somebody caught that last week. Who caught that? Lily caught that. Yep, and Ella, I think it was Ella. Yeah, it was Ella. Yep. So that was just that's a typo. It's actually the correct lab for today. For last week, if it's the one about what was it called? Do you remember what it's called last week?
Acid base titration of an eggshell.
Oh yeah, titration of an eggshells today, and the drip drop one was last week. Got it. Okay.
Did you guys get a different fish?
I did. You noticed. He's not very. I hope he's alive.
Did the other one die?
Okay, so this is weird because he's not looking great this morning. Yeah, the other he might be dead too. This is making me crazy. The other one finally died. This sounds terrible, but Herschel was like, this sounds awful. Forgive me. The fish that never died. Like he was the saddest thing. He ate his own tail, and I caught him laying upside down multiple times. And I'm like, oh, he's dead. And I'd move the thing, and he'd swim. So I got him a couple days ago. No, he's just sleeping. This is I'll show you guys. This is
literally almost every time I came here, I would feed the fish.
Ooh,
oh yeah.
Oh, no,
This is what I find him in there. Where'd he go? Where is he in there? It's hard for me to aim this camera at the back of this computer. Oh my gosh, this is tricky. Hi. Why is it so hard for me to find him? Oh, here we go. Can we see him in there? Nope, we can't see him yet. I cannot make this camera aim. Let's see if I can angle it a little.
Wait to the other side.
I know, it's so weird.
Other side.
I know, I'm trying, but I suck at
That
this.
side. That keeps.
No, that's not the right side.
Yes, it is.
Oh,
Look at it.
but it's all mirror image, so it makes me want to. I'll switch it back. Just turn it around. I can't think in mirror image. But so our last one was Herschel, because I name all my fish after scientists. This one is Antoine. Can you see him now?
no.
There he is. For Antoine Lavoisier. I named him for a chemist since we have so many chemists this year. And he's very pretty. He's chilling. I think he's just sleeping. All right, so titrations. So titrations are so cool. And I think you'll really enjoy them. The one we're doing today is without a burette, and it's going to involve using a dropper. And you girls at home are going to be thankful probably that you're watching it on video and not trying to do it, because you have to do very exact dropping and you have to count without missing any drops. What you got?
Never told us what happened to your fish.
Oh, well, he was dead. He very much died. I cleaned his water, and he did the thing again where he laid on the bottom, and I thought he was dead, and I moved it and he swam. And then the next morning I came down and he was laying there again, and I was like, oh, we finally decided that it was time to go to the big fish tank in the sky. I mean, nice fish, but the one I had before, Copernicus, was smart. Like he would come up to you, he'd wave his little fins, like, oh, feed me. He was attentive. Herschel is just not so with it.
Yeah, I think my sister had a fish once. She bought this like pretty big tank, like bigger than that.
Yeah.
For like was it beta fish? I think.
Yeah, that's what this is. Uh-huh.
Yeah, I think they usually, she bought, cool fancy tank,
Mm-hmm.
fancy, little decorations. But it looks like I think a year. Maybe.
Oh, yeah.
It was like,
Well, I've had some betas that have gone 2-3 years. So, all right, so let's look at titration. This is titration, and it's super cool. So basically the way titration works is it's an analytical method that you're going to use to, Ozzy, quit licking my thumb, in which a standard solution is used to determine the concentration of an unknown solution. So what's a standard solution? A standard solution is one for which you know the exact concentration, usually molarity. So it's a quantitative analysis. So that means it involves numbers, and you're trying to find out how much if it's quantitative. It's a quantitative analysis of acids and bases. And through this process, an acid or base of known concentration, so that's your standard solution, is used to neutralize an acid or base of unknown concentration. So when you set up a titration, like today we're using a dropper, but if you're using a burette, you set it up like this and you can see the burette right here, right? And then you usually have a conical flask, which is actually an Erlenmeyer flask. And the reason you use an Erlenmeyer flask is because you have to do some swirling. And that's what they're made for. They're made for swirling. So in here, in the burette, you have an acid or a base of known concentration that is called your titrant. Okay, and your titrant is, you know about it. You know how much there is, you know the volume, and you know the concentration. And the titrant is dropped drop by drop into what you either call your analyte or your titrand, which is so fun, titrant and titrand. Like that's not going to confuse anybody, right? Or your analyte, whatever you want to call it. And you count these numbers of drops, or if you're using a burette, you can measure exactly. And by doing that, you then can determine the concentration of this fluid because you're going to use an indicator. You guys remember indicators, right? We used an indicator last week. What color did it turn in the presence of base? Do you remember? Yeah, pink. Yeah, it's phenolphthalein, which we're using again today. So titration process can be monitored by visual indicators. That would be something like phenolphthalein, or pH electrodes, or both. And it's so fun. Oh, who's in here? Yes, chat. Who's in my chat? Are we doing something on a page? Kind of. We're just kind of working through the lesson a little bit at a time. Not so much page by page, but more idea by idea.
If you want like a fish pet, or like that'll live for 15 years, then you should get an axolotl.
Oh yeah?
They're really cool. You just need a 10-gallon water.
Axolotls are cute.
Yeah, they're really cool.
So here again is just another titration setup. So you can see it again from a different angle. So you have your titrant, that's your substance of precisely known concentration. You can also call this a reagent. Sometimes you'll hear the word reagent used, and it's always going to be in a chemical reaction, or your reagent's always going to be in your reactant side. And you add it to your titration, and then it's also your standard solution, which is, these are just words you can use interchangeably. Titrant is a standard solution, is a solution of exactly known concentration. And remember, we talked about how concentration can be anything from like milliliters of solute to milliliters of solvent, or milliliters of solute to milliliters of solvent plus solute. And then it can also be grams to milliliters. So the way to do it, do you guys remember what unit we use if we want to be very specific so we don't get confused about our concentration? We use molarity. You see it as a big M, molarity.
Nanoliters.
Nanoliters, yeah. And then you got your indicators. So that's how your indicator works, right? You guys saw that last week. Some of you were able to get your indicator one drop so that it was just a very pale color like this, and you knew right then, ooh, stop, it's perfect. And that's what you're doing today. You don't want it to get bright pink. Today you want it to get barely pink, and then you know you're on track.
Didn't you guys argue in Spanish class about something over colors? Oh my god. This is gonna be bad. You guys are gonna be like, oh, this is light pink. No, this is violet.
Oh yeah.
This is color.
So then we have something called an equivalence point. Okay, and your equivalence point is the point at which your, what's this molecule called right here? H3O plus. Do you remember?
Water.
Hydronium. Hydronium. And how is hydronium produced? Do you remember? Remember that acids donate hydrogens.
Oh, an acid probably donated a hydrogen
So
to the water.
yes, Alex, so an acid donated a hydrogen to the water. So if the water's hanging around there and the water is H2O and it bumps into another hydrogen here and you get H3O plus, you have your positively charged as a proton donor, so positively charged hydronium. And then what was the OH negative? Hydroxide. So hydronium goes with acid, hydroxide goes with base. This is one of the things you want to know, like no. I'll always tell you if there's something you really want to know and keep in your brain like forever, or at least all the way through high school or college if you're doing chemistry in college. Hydronium and hydrogen go with acid, hydroxide goes with base. Anything that ends with the suffix hydroxide is a base. You'll hear it all the time. You'll hear something hydroxide, and you know it's basic. So your equivalence point is when your amounts of hydronium and hydroxide when equal amounts have been added, exactly equal. And that's indicated by the color change. And sometimes it's pretty dramatic. Your end point, so these are very similar. Ooh, I have a weird space. Your end point is when your indicator shows that the amount of reactant necessary for a complete reaction has been added to the solution. So you got a color change here, but this one shows that the right amount of reactant has been added necessary for a color. So what does this mean? How are they the same and how are they different? They sound pretty similar, right? So look at the graph, because this is a good graphic. So what do we have on this side? What's on our y-axis? pH. And what's on our x-axis here?
The volume.
The volume.
How many moles is it?
Yep, volume of 0.1 molar sodium hydroxide. Okay, so you see what's going on here? We're trucking along and we're trucking along. This is the equivalence point. Okay, so if you look right here, we have different indicators. This one's methyl orange, and it indicates a pH range of like 4.4 or something to 3. Then we have litmus paper, and it indicates a pH somewhere between 8 and 5.5. And then phenolphthalein, which is what we've been using in lab, indicates a pH change of about 8.5 to 10. But right here at 7 is the equivalence point, because at 7, this is when it is completely neutralized, right? But your equivalence point is up here. This is when you see the change in color, because your indicator may not fall within a zone where you have 7 as a possibility. Do you see what that means? So if you've got your hydrochloric acid and you're dropping your sodium hydroxide on in drop, right here, you've completed the reaction. It's now neutralized. This is your equivalence point here. And then for a pH of 7, but this equivalence point is the pH of 8.27. This is the one you're going to see because this is the indicator you're using. So the point during a titration where the indicator shows that the amount of reaction necessary for a complete reaction has been added. I don't know why I have a weird thing there. So the difference is, the main difference between the equivalence point and the end point is that the equivalence point is the point where the chemical reaction comes to an end. And the end point is where the color change occurs in the system. So if you can remember, equivalence point is when your reaction is done, it's equal. Equivalence means equal. You have equal amounts, right? End point is where your color change occurs, and that means you're done. I can end because I see that something has happened here. I have a visual indicator. So that's how your equivalence and your end point are different. That's not going to be something major on your test, but because they are a little confusing, but you get the kind of the main idea. So then you have a transition range. If you look right here, this is another, you can see it in this graphic actually that we just looked at. Nope, not that one. Go back. See here that each of these has a range. Here's your methyl orange range, pH range, litmus paper pH range, phenolphthalein pH range. So this is because all indicators have a transition range, okay? And that needs to match the endpoint pH as closely as possible in order to minimize titration error. So this means that you have to choose the right indicator for whatever titration you're doing. And that means you have to have an understanding of the pH of the acid and the base involved in your reaction. So indicators do not change color precisely at one pH value. Instead, they change color over a range. And the color of the indicator is going to continuously change. So with the phenolphthalein, it'll go from very pale pink to like super bright pink, almost purple, right? And the range is different for every indicator. So you have to have the right indicator for your particular experiment. And the transition point of an indicator is defined as the point at which the acid and alkaline, remember alkaline means base, forms of the indicator exist in equal concentrations. So if you look right here, so here's methyl violet. All right, so if you were trying to work with something that had a very, very acidic pH, it was very low, like 1 or 2, and you wanted to see, well, less than 1, like 1 or 0, and you wanted to see if you could make it slightly more basic. Like say you had super duper a bathtub full of super duper concentrated hydrochloric acid and you wanted to add sodium hydroxide to it, milliliter by milliliter, you would want to use something like methyl violet because it's going to start to change when it's still very acidic. But likewise, if you were using something super basic, this may be a good one for you. And I don't think I've ever used alizarin yellow, but that's interesting. I have bromthanol blue, I have phenolphthalein, I have methyl orange. These are the ones I have upstairs. So you can see that they're all different, right? And that's the point, is that you just need to pick the correct indicator for your particular experiment. So did we watch this acid-base titration with our friend Professor Dave?
I think I did.
Yep.
I did.
And then, so what was the equivalence point? Do you guys remember?
I'll give you the exact definition.
Well, let's watch and see if we can find it
It's around second 40. He did give us a definition.
in his particular example.
So you can skip to like 30 seconds.
Skip to like 30 seconds. It's not a very long video, I don't think.
Or it's shorter when you put it on 2 times speed. Add block for YouTube. It's better, 'cause you don't have to watch like 30 seconds.
Where is that?
No volume.
Why don't I have volume? I
You can do
should.
subtitles.
No, it's just weird. I don't understand why it gets strange like this. You should still see it on my computer is the thing. Maybe not. Oh, great. Professor Dave's going to be silent this morning. Ugh.
Well, no, it's because you're on mute. You're muting it. See? Press N on the keyboard.
He's not, well, he is now, but see, he's still not talking. That's I had him muted. That's okay.
No, I'm not.
So where was it? It was around
Oh,
where?
that's because the volume's not.
No, it is.
No, we're good. See, look.
It's right here.
A bit less, I think.
Still can't.
Maybe not.
Oh, wait. I can hear him a little bit now. Hang on.
You can hear my little
Amount of acid.
There, we got him.
skip raptors.
When we
Hold on. Here we go,
perform titration,
Professor Dave. Gotta love him. He's so fun.
Acid-base titration aim of determining how much acid or base is present in solution.
Oh, I love
by
it when the
determining
audio track is
precise
off. It's so
volume
fun.
Of acid or base that will completely react with it. It's like a kind of stoichiometry. On a titration
Yo, Dave.
That's right.
for an acidic
That
solution,
happens for me too.
pH is plotted against the volume of base that is
It
progressively
would
added.
speed up really quickly, and then
You're
just
being
As
weird.
add base, the
until you
pH
get
slowly
to the water.
rises,
It
then
starts
sharply
to-
rises towards
There he
the
goes.
equivalence
It's
point.
annoying.
This is the point where precisely enough base has been added to neutralize the exact amount of acid in solution.
So there
When
you
we
go.
perform titrations, we recognize the
So
equivalence
that
point by
was
using
his
something called an
definition
indicator.
for equivalence point.
Point where precisely
The
enough
point where precisely enough, what'd you say, Alec?
base has been added to neutralize the exact amount of acid in solution.
That's right. A point where, I have it written down. The point, equivalence point is the point where precisely enough base has been added to neutralize the exact amount of acid in solution. So that's your equivalence point. So this was your homework piece, right?
Yeah.
Excellent. Good.
Exact definition.
Huh?
Do you need to turn that in?
What did I say? What does it say on the front of that lesson? Does it say turn it in?
It just says do, and then
If it doesn't say keep in binder, then
it
it's,
doesn't.
oh no, on the front page, on the syllabus little excerpt.
Oh, I have no idea.
Well, let me show you guys as well then. We're going to take a minute and we're going to go over our study guide, right? And I'm going to put this up for you guys to work from as well at home. These are the things you're going to need to study for your test, which is coming up this week. Okay? These are the things I am going to, cereal. Yeah, and I left them in the slideshow because I know for me, it helps to have a visual to connect to it. Okay? So this is the mixtures and solutions and acids and bases unit 7, right?
Lucky Charms.
Lucky Charms, I love Lucky Charms. I never buy them and I really love them.
I've never had them.
What?
I love the marshmallows, and that's why I eat all the cereal
Oh
and then
yeah, they're so
marshmallows and
delicious.
just shove all of them in my mouth.
Oh yeah, this little freeze-dried marshmallows are just the best. They're pure junk.
We have like a whole bag of those freeze.
Oh yeah.
Breakfast, it's overrated.
So what's a mixture? Who can describe a mixture to me?
Oh,
Oh, Jocelyn, go ahead.
Yeah.
Oop, does she freeze?
no.
Oh, okay. No, substance made by combining two or more different materials in such a way no chemical reaction occurs, right? There's no chemical reaction in a mixture. And at
No.
the same time, you can usually separate it back into its original components.
Right.
So that apothecary jar over there next to Ella is a great example of a mixture. What's in there, Ella? Yeah, what's in that?
Keys, marbles, little rocks.
Yeah.
Coffee rocks.
All kinds of stuff. Marbles, little beach glass, keys, some buttons, some springs. That's a mixture. I don't know. I thought it was cool.
I got a mixture of different Legos.
Oh, that's cool. Yeah. You got Lego. Is that like one of those little ornament bolts?
Yeah, it's a hollow plastic ornament that I colored with Sharpie.
Excellent. Did you have a question, Alec?
Is that actually a mixture? Because you can actually get the sugar back if you're making simple syrup.
So that's still a solution because it's dissolved in there.
Yeah.
But when we talk about concentration, remember we said you can increase the concentration of a solution by removing some of the solvent. So that would be like if you evaporated the water somehow and the sugar was left behind. So types of mixtures. So we have homogeneous mixtures, and those are ones in which the particles are distributed evenly, right? They're not easily separated. And then we have heterogeneous mixtures. So what is the jar? Is it heterogeneous? Yep, heterogeneous, very much heterogeneous. Homogeneous, there are other types, right? Heterogeneous is just kind of heterogeneous. So when we get into homogeneous, there are types of homogeneous, remember? All right, so you have suspension. So suspension is a mixture of fluid that contains solid particles sufficiently large for sedimentation.
That's gross.
Do you know what that is?
It's chia seeds.
It's chia seeds. Yeah, of course you guys know. You
I
don't
did not
don't have
know.
Lucky Charms at your house, but I bet you have chia seeds. They're like, oh my gosh, I love your
I
mother.
love putting them in my cereal.
Oh, do you? Okay, yeah, they're kind of slimy, but yeah, there's the chia seeds.
It looked like the little magnet eggs or something.
Yeah. Have you ever made well, okay, a great example of a chia pet. Yeah, we talk about suspension in earth science when we discuss like a flowing stream. There's usually sediment in the suspension, so there's usually some particulate, some bigger than others that roll along with the stream. That's how river rocks get really smooth, right? Because there's sand suspended in the water flowing. And it's a mixture, and it's pretty homogeneous because you're not just going to go like pluck chunks of sand out. It's all evenly mixed, but it rubs over those rocks and smooths them out over time.
Orange juice or lemonade with like some kind of pulp would be.
Yeah, if it had a lot of pulp in it, yeah. Pulp is a good example of something that would sediment, that would sufficiently large enough for sedimentation. So then you have colloids. So colloids are mixtures with really small particles, and the particles are distributed throughout, and they're usually surrounded entirely by whatever other materials are in this particular mixture. So if you've got milk, for example, that's a great example. You've got sugar and you've got fat, and everything in it, excuse me, is really, really small, and it's all kind of evenly distributed, and each particle of whatever substance is pretty much surrounded by the particles of the other substance. And then you've got, lastly, your solution. And this is where we get into a lot of chemistry stuff. So it's homogeneous, it's two or more substances. What gets dissolved and what does the dissolving?
The solution gets dissolved, the solvent doesn't.
The solute gets dissolved, yep, and the solvent does the dissolving, and together they form a solution. So do you know what this one is in this picture?
Sprite?
Yeah, anything like that. Could be Sprite, carbonated water. In that case, your solute is a gas dissolved in a liquid, right? So solutes and solvents. So your solute is dissolved, your solvent does the dissolving, right?
That's cold water.
Yeah, that's very cold water. So it probably won't dissolve as much sugar as it could if it was warm water.
You could just stir it a while. It might get so.
So if you want to dilute a solution, what's something you could do?
Add more water.
You could add more water. Yes, solvent. Yeah, it might not be water, so it could be I'll add more solvent would be a better way to put it. And if you wanted to concentrate a solution, what could you do?
Add more
more
like
solute.
other stuff.
Add more solute. And there's one other thing you could do.
Oh wait.
Take out some of
Take out some of the solvent. Ella, good job. So yeah, so you could add more solvent to dilute it, and you could add more solute, or you could remove some solvent. So a good way to remove solvent is to usually boil something. That's a great way to do it. Turn it into a gas. That way you can get some of that solvent out. Okay, so remember that solubility is affected by pressure, temperature, type of solvent you used, and the surface area. So temperature was what Alec just pointed out. That was a ice cold water in that pitcher, and it is not going to do as good a job of dissolving as it would if it were warm water, right? And why is that? Because what happens to the particles in a substance when you heat the substance up?
They expand.
Yeah, they get a lot of energy, right? They start bumping around. They're more likely to dissolve something if they're banging into it. And then only one state of matter is really affected by pressure. Which one is that? Gas, right? Gas is really the only one that's affected by pressure. The type of solvent is going to matter. And then your surface area. So look at this sugar cube and then think back to a second ago, we had that little bowl of sugar. Which one is going to dissolve more quickly in room temperature water? Yeah, the bowl, because in this case, you've smashed all these little sugar crystals together. In the other case, when they're separate, you've increased their surface area. The more surface area exposed to the solvent, the more quickly it's going to dissolve, more efficiently it's going to dissolve, right? And when we talk about how what matters with the solvent, we say what? Like dissolves like. So remember that like dissolves like. Anybody ever put on Halloween makeup that's oil-based and try and take it off with water?
Yes.
Doesn't work, does it? What did you have to use to get it off?
My mom's makeup wipes.
Mm-hmm. And they have something in them that is non-polar, like an oil.
I've never done that before. I just wore the giant dinosaur costume.
Yeah. So you can use something oil-based to take off something oil-based. So if you have oil-based makeup on, Halloween makeup or whatever, and you need to remove it, you can use baby oil or makeup remover, like Jocelyn said, or cold cream. That's really good too. Cold cream used to be something that ladies used to use a lot, probably back in like the 50s, 40s, 50s, 60s. But it's a really thick, almost like a pasty lotion, and it's oil-based, and you can slather it on, and it pulls off all the.
If you want a blood stain, like I have a blood nose, my mom told me to wash cold water over it.
Yep. So yeah, it just kind of depends. Oh, is that those are my mourning doves. They're a mated pair. They're pretty. They hang out together. So like dissolves like. If you're trying to dissolve something that is polar, if you have a polar solute, you need a polar solvent. And if you have a non-polar solute, you need a non-polar solvent. So remember that your polar substances are polar molecules and ionic compounds, like NaCl is an ionic compound, right? Salts, water dissolves salt because water is polar. And then your non-polar substances dissolve your non-polar substances. So those are your organic compounds and your non-polar molecules. You ever had a shot that isn't in your muscle, it's just in your fat? You ever had one of those? Sometimes you get a little shot and it's just in your, or you've probably seen people do them. They pinch and do just their belly fat. It's because whatever is in that dissolves in fat, they don't put it into your bloodstream or whatever because it doesn't dissolve in water, which is mostly what your blood is. All right, so then we had degrees of saturation. So you guys know this: unsaturated, saturated, supersaturated. You guys know what those mean, right?
Supersaturated is basically loose sodas.
Yeah, so unsaturated, it's more solute, then you can still dissolve more solute in it. Saturated, it can't dissolve any more solute. It's done. And it'll probably start leaving some solid crystals on the bottom. And then your supersaturated is where it's so saturated that it starts to form crystals on its own. Remember when we did we had like some people called it cold ice, but we dripped it or tapped it and it turned solid because it was super saturated, and all it needed was just enough kinetic energy to align the particles correctly. And then they just turned into a crystal lattice really quickly, which was super cool. So remember that acids are proton donors and bases are proton acceptors. Got to remember that. Acids are proton donors. It goes with hydrogen and hydronium, H3O plus. Bases are proton acceptors, and they go with hydroxide.
The test is today.
No, it's due next week.
Well, we can do it today.
You can do it today. It's open. Yeah. And then substances with a pH range. In this pH range are acids, right? Anything over here is an acid. And in water, what do acids form? hydrogen or hydronium ions, remember, and here's your base over here. So you have your hydrogen and hydronium, and then you have your hydroxide. If you can keep those together in your head, you'll be good to go. Hydrogen and hydronium versus hydroxide. So I'm going to put this, when I send out today's email, I'll make sure that there is a link for this, or I'll tell you where I've put it. I can't just figure out where I'm going to stick it so you can access it easily. But I'll put it somewhere so you can. And you guys can practice for your test, study for your test by going over this. It would be good if you had somebody to practice with you who can sit across from you and ask you the questions. That way you don't see the answer right on the page. It's not a terribly long test. It's 20-something questions, so I don't remember how many.
Easy.
Yeah, but it's been kind of the long and weird unit,
I remember my
you know?
the start of my midterm. I had midterms in 3rd grade.
Yeah.
So my math midterm in 3rd grade was literally 50 questions. I just skipped recess to do it.
Oh my goodness, really?
Yeah, because
Wow. So anybody have any questions about Unit 7 test or today's
Can I have the
lesson?
answer key?
Can you have the what?
Answer key?
No. No answer key. You guys are too crafty for me. So we're gonna go do lab now, and I'm gonna let you girls go. Y'all have a nice, you stay warm, keep your grandparents warm, Jocelyn and Senya. I'm glad to hear you're back to dancing. That makes me very, very happy.
We got a wood stove, so we're good.
Oh, yeah. So what, Nello? 25?
I have lab 24.
Yeah, it's actually 25. It's yep, that was what you caught last week. It was, yes. You don't have it at all? What's there? What's the one you got your hand on? The other side. All right. Well, we'll look at it. We'll see you guys later, okay? Bye, y'all.
There's no lab 25.
Bye.
It's just 24.
It says 24, but it's in your, look at the bottom of your page.
The 24s, the second, the one, it should, one of them
No.